Sometimes it hangs, but let's see. Okay, seems to be working. Okay, great. All right, then I'll start the recording as well. Okay, so all right. Hi everyone, and welcome to yet another event from our interest group in privacy and machine learning. Yeah, so really happy to host Luca today from University of Cagliari, and this is by no means a collusion post Euro Cup win. This talk by an Italian speaker was scheduled before anybody, including me, even thought Italy could, get to the quarterfinals. But anyway, so we're really happy to host him. For those who don't know Luca, he's a postdoc at the University of Cagliari. He's done his studies, MSc and PhD in Genoa, and he's done a lot of work on adversarial machine learning with an application to the cybersecurity domain. And that's really what he's going to talk about today. As you can see from the title, we're going to talk about adversarial Windows malware. So Luca has kindly asked for people to ask questions at the end. So you're welcome to do it on the YouTube chat or on the Zoom chat, or at the end, we'll stop the stream and we'll stop the recording. And you can just unmute yourself, and if you want, turn on your camera and ask questions, so we can have sort of a discussion, more informal, nothing recorded, sort of a Q&A at the end. Yeah, without further ado, thanks, Luca. Take it away.
Okay, so thank you everybody for being here. Thank you for inviting me. So I'll start with talking about let's say a summation of our latest work, which is adversarial EXEmples functionality preserving optimization of adversarial Windows malware. And let's just dive in. So, okay. So just for giving you the context, we are talking about taking machine learning technologies and applying to the security domain. And that's kind of the trend that has been basically, that has been basically seen in the past for images, where they just understand that deep learning is very, very useful for taming very, very difficult problem like image detection. And then they say, okay, we have like tons of millions of malware, we might do the same. So that's what they are doing right now. So you take deep learning technologies and you take like millions and millions of data and you train classifier with the hope that your model is really learning a good representation of malware, as they did for image. And then these things works somehow. And what they're doing is that they're also like selling them. There are many companies that are already applying deep learning and machine learning technologies in production to stop malware. But topic of this talk, who could have guessed? Also, these things are vulnerable to adversarial attacks, as the same for images, but with some caveats. So which are the difference between images and malware? First of all, we are dealing with input space manipulations. So we want to perturb something and we want to run something because we have programs. So what would you have done with images? You would take an images like this, you would have some adversarial noise, and ta-da, that's an adversarial example, and it's with high confidence misclassified by the network. Then you want to do the same with malware. So you take your program that is it's malware because it has a very, very high confidence to be malware. Then you add some noise and you produce something, and that thing might not work anymore because altering bytes is not the same as altering pixels. You might end up with files that are entirely corrupted. So that's the first problem. Second thing is that, okay, what we can do to bridge this gap? What we can do to create adversarial malware that are not broken while we create adversarial examples. We take our malware and we perturb it somehow, and let's just forget about what is this perturbation, and then we put it inside the sandbox. And what we do is we run the malware and we say, okay, this malware is still working. So I can repeat the process of the perturbation and just, rinse and repeat until I create an adversarial malware. But this approach has one cost. That is, you have to put the sandbox there. So you have to reset the sandbox at every iteration, and you have to wait for the malware to express its malicious behavior. And maybe that will be not possible because there are malware that try to detect if they are inside a sandbox. So that's might be tricky. Also, another thing that happens is that now there are like many works that are trying to create adversarial examples in the malware domain, but the reproducibility is kind of difficult because there are some code here and there, but are difficult to be tested, and the results are not always so reproducible. So it's not easy to to start again doing the same things that others did. And then again, many attacks use basically common things, like common concepts, but there is a lack of a general process saying, okay, for doing an adversarial example in malware, you have to do this, and that. So to breach this, so just to recap, the problem are two. The input space attack are very, very difficult to do because you can break the malware. And also, like the state of the art, people just used like trivial things like padding, so adding content at the end because they don't know how to deal with the file format. And then there is the problem with the sandboxes and the reproducibility problem that I told you before. So as a contribution, what we bring to the table is what we call functionality preserving attacks that are based on manipulations that are either not trivial, that you can use for alter the representation of the program without destroying its format, so it's still runnable, and you're not changing its functionalities. And also, since you're doing that, these kind of manipulations avoid the usage of a sandbox for the attacker, and it's helping for like saving computations. And then what we do is that we basically create a framework called RAMEN, which is general enough for creating new adversarial attacks, but also for recasting older adversarial attacks inside it. So you have really like, a pipeline. Okay, you have to do this, and that, as I told you before. Then we create a Python library called SecML Malware, which is open source, and it's already including some of these attacks in the state of the art and our novel attacks. And you can use it for like testing the robustness of your malware classifier. On top of it, we also create a command line tool called ToucanStrike that you can type things and you create like adversarial malware directly on your shell. So let's dive into this general framework called RAMEN and how these things work. The two main components. First, you need to apply these manipulations, and then you have to optimize the manipulations. And basically what you want to do is that you either want to minimize your goal. In this case, our goal is formalized as loss function that takes in input a malware, which is Z. And this malware is perturbed by this manipulation H. And these manipulations are somehow parameterized. And we're going to see later what this means. So you want to minimize this loss. This basically includes also the score that the classifier you're attacking is returning in output with the sample you send to it. And then another thing you want to do, you want also to constrain the manipulation you're imposing by penalize them somehow with a cost function. So this is the goal we want to minimize. And the problem is how we perturb these things. What is the H function? What is this parameter T? Let's deep dive into that. So we introduced the so-called practical manipulations that are these functions that preserve the functionality of the program you're passing input. And that is how you basically avoid the usage of sandbox. And these manipulations are parametric. So this T vector is basically a vector of parameters that basically encodes the intensity and the nature of the manipulation itself. Since it's a vector, and since we are in the case of minimization problems, what the attacker can do is that, okay, I can tune this T and basically reduce, enlarge, and change the manipulation I am applying. And then these manipulations are cumulative because if you're targeting, you know, the structure you're using, like the file format, you basically can do not only one manipulation, but in principle, you can stack them. And just to give you a very, very brief example and give you the intuition, an example of this H function for images might be rotations. So imagine T as the degrees of the rotation. And then if I basically apply this function, I'm asking for a 90 degrees rotation. Of course, this is images, how they bridge to malware. For doing that, I firstly need to introduce you the file format that is used for storing programs as regular files. This is the Windows PE file format. I don't know how many of you are like familiar with that, but I'll just give you like a short recap for filling the gaps. First of all, it's made up from several components. The first one is what you can see here, the so-called DOS header and stub, which is basically a chunk of byte that is replicated in every program that is compiled on modern Windows operating systems. That's basically said to a DOS environment that that file is not a DOS program, and that's it. And you have this kind of thing in every program in the world. Strange. Then you have the real header, that is a PE header, that contains the real metadata of the program, followed by, again, unlucky in the naming of these things, optional header, which is not optional at all, that describes to the loader where it might find like the code, the data, and all of the other things. And finally, we have the key components of the program, that are the sections, containing, again, the code, the initialized variable, resources, and many other things. So this is kind of complicated. I mean, you see, like there are header, and there are sections, and then there's the code. So it's not easy in principle understand. I mean, it's not easy to understand where you can mess around with this thing. So let's try to understand what the attacker can do to mess with this format. First of all, remember the useless thing that I told you about before? Well, it's not useless at all. I mean, not from the attacker perspective, I mean. So what the attacker can do is that it might alter partially or completely this header, just saving like the relevant spots that are the magic number, MZ, at the very beginning, and the offset to the real PE header. So the attacker has basically some hundreds of bytes at their disposal to place the adversarial content there. And we're gonna see that's kind of, I mean, it's something small, but that's useful. Then what you can do is that, well, since there is a pointer from the header to the real header, what you can do is just you can abuse this pointer, enlarge it, making space, and do what I told you like 1 minute ago. So you can just extend the DOS header and just write in this DOS header. Then again, since the optional header points to the sections, what you can do, you can again abuse a pointer, enlarge the space between the first section, or this is general enough for every section, but just for getting things a little easier, you just shift down the first section, and then again you have how many bytes you want for placing adversarial content. Then what you can do again, you can add new sections. So you add an entry in the header saying, hey, loader, there is a new section there. And then you add, how many bytes you want. And finally, last but not least, you have padding. So if you don't want to do any of this complicated stuff, you just want to append the things at the end, that's it, you can do it. So these are some of the practical manipulations that are around and how they can be parameterized. So imagine you have this T vector of parameter, and basically when you pad it with this T, you basically take the bytes that you're listing and you put it at the end of it. So depending on the size of this T, you're basically deciding the size of the manipulation. And for the partial DOS manipulation, that is like, again, writing in the DOS header, what you can do is the same. So after the MZ, you put your adversarial content. So if you don't want to basically alter all of the DOS header, but just some of them, you can specify this in this vector. And in this way, you can tune the amount of manipulation you're adding. So I hope I gave you the intuition about how you can perturb malware without breaking it. And now there is the second part of the framework, that is how we optimize these guys. I mean, how we optimize the bytes we're going to inject inside the malware. So the very, very super naive thing you can do is you can just query the model with a gradient-free optimization technique, like, let's say, a genetic algorithm. Why? Because you just don't care about the internals of the model. You just want to create adversarial malware. And you don't want computed gradients. You just want to, like, you query your target n times, then you update your parameters, and basically you change the manipulation, and then you rinse and repeat. So these are byte per byte optimization of the payload. These, of course, has problems, because imagine that you want to inject like 1K of bytes. It means that your black box algorithm needs to optimize 1K bytes. And this is very, very computational expensive it's computational expensive, and it's query inefficient. So if your target is your machine, no problem. But imagine if your target is like on a remote service, views total, for instance, and then you're sending like 1K query. That's a lot. You're gonna be like detected, and you're gonna take like a lot of time to optimize this guy. And also the problem is that imagine that you, in your adversarial payload, you want to produce the string hello world. With a blind search, it's going to be very, very tough to produce such precise pattern, because you're going to need like a lot of queries to basically guide the optimizer to find the hello world string among this giant space of all possible strings. So how can we tune these limitations? That's our lucky day, because we basically propose an approach called Gamma, which is a genetic algorithm that, instead of optimizing one single byte at a time, it optimizes chunks of bytes that are taken from goodware. So imagine you take, let's say, Microsoft Paint or Word, and you extract n bytes, and then you let the optimizer decide how much of this content must be injected inside the malware. And this also allows us to reduce the size of these parameters from 1K to, let's say, 10, because I just use 10 sections from this goodware, and that's how I parameterize. So the optimizer is, we are helping the optimizer, because now the space is very, very tiny, and in this way we reduce the number of queries. So how Gamma works? So let's take like the section injection. So I am adding a new section to the program. If I apply this T with the goodware that I want, I'm basically asking to add to the malware in input like the 20% of the first, 70% of the second, and 30% of the third. And that's our adversarial malware. In the space, maybe here we also injected 500 kilobytes, but the space of the manipulation is just like a 3-dimensional vector. And that's it's a good compression for our needs. Okay. Then the point is, I've explained to you like how you can manipulate and whatever, but what if now I want really to create an attack? So if I want to create a query attack with my formalization, I have to define 3 steps. First of all, the loss I want to minimize. It might be the score of the classifier, the score plus a penalty term, and whatever. Then you have to define which manipulations you want to use: padding, extending, content shifting, yada, yada. And then finally define an optimizer, because we are in a black box technique. So we don't know nothing about the classifier itself. So an example, just to implement like Gamma, so the algorithm saying that I said to you like 5 seconds ago, and we want to use padding, well, that's our step. So we choose the loss. In this case, it's the score plus the penalty on the size of the manipulation you're using. Then as manipulation, you use the padding. And finally, as the optimizer, we use this genetic algorithm that injects goodware content. And tada, you have your adversarial attack already. And that's exactly what you did with the state of the art. So you basically, with just using these 3 things, we can recast almost everything that has been proposed. And I just give you like here some examples, like people using reinforcement learning agents, or just again genetic algorithms with different kind of manipulation and different kind of loss function. Okay, so I hope I convinced you that query-based attacks can be good. And now we transition to, for the mathematicians here, we now switch to gradients. Like, can we exploit, I mean, if you have your model like here, what you can do, I mean, I can compute gradients as for images. So this is the ideal case. I have my T parameters, and I really would like to use directly gradient descent on it. So what I do, I take T, and then I just sum, I mean, learning rate multiplied the gradients with respect to T of that thing. That's the ideal case. But I mean, it's not as easy as it seems. The problem is that in this security domain, most of the feature extractors that are hidden in this formula are not differentiable. Imagine like an aggregation function. That's not differentiable at all. And the same thing happens for the practical manipulations. These are not differentiable. So how can I solve this thing? Well, the idea is the model itself, let's think about a deep network, is differentiable, but it's differentiable up to the feature extraction layer. So what you can do, you take your sample, you shoot it inside the feature space, and then you optimize with gradient descent. Then what you do, you arrive basically here, and then you want to reconstruct this sample inside the input space. And then you basically apply another optimization to find the T that best, that creates a malware that is close enough to that point in feature space. So this complicated thing is depicted in this picture. And basically, let's say you want to do a padding attack. So you take Z, your program, and then you add the padding, that is the yellow thing that you're adding to the, to the malware. Then you put it inside the feature space and you apply gradient descent because you're minimizing that function in the feature space, and that things there are differentiable. Then you arrive at X star that maybe is already an adversarial example, and you try to reconstruct it by finding the best T that produces Z star that is close enough to X in feature space. So this, and then you repeat the process until you find an adversarial example. Okay, so here there are more steps to implement with respect to the black box attacks, because okay, you have to define the loss function, and you're good with that, and then you define the manipulations, and again we are good with that. But then you have to define two more steps. First one is how you do gradient descent on feature space. So you need to say this is the optimizer I want to use. So gradient descent, ADAM, and you can think about every possible thing you might want to use. Then you have to define a strategy to use for reconstructing the sample after you conclude the gradient descent. So just for giving an example, you want to do the DOS header attack. You fix the loss, that is just the malware score. Then you fix the manipulation, that is the DOS editing of the program. In feature space, what you do is say, okay, I just don't want to use gradient descent. I just want to take just one step in the direction of the gradient. And imagine this attack that encodes the byte in some sort of space. Then for reconstructing, what you do is you take a step in this strange space, and then you say, okay, this object, how much is similar to one byte in the input space? And that's how you reconstruct. So of course you might lose some confidence for the attack because there is this reconstruction step. But that's the only thing you can do, because otherwise you're going to end up with a value that is not connected to anything. Okay, and these 4 steps are the only 4 steps that you need for, again, recasting most of the attacks inside our framework. Here we have the work that we did and other previous and contemporary work to ours that use different different strategies and different feature space optimizer, like the fast gradient sign method, for instance. Okay, so I hope I convinced you that you can basically use our framework to encode both black box gradient free and white box gradient based attacks. Then, a natural question will be, yes, but then what I have to do in practice? Well, in practice, you can test the robustness of your solutions with our library, that is SecML Malware. So it's a Python 3 open source library that is written by us, maintained by us, and used by community. So there are I mean, it's taking momentum, and I'm kind of happy because, I mean, I'm spending a lot of time in these, I mean, doing these things, and I'm happy that these, I mean, I'm seeing that this is becoming useful, and that's, I mean, I'm very proud of this work. And SecML Malware contains already some of the proposed attacks in the state of the art. So our attacks and other, like, I mean, FGSM attacks. On top of this, we also implemented this ToucanStrike, which is a command line tool for testing. And at the end of the presentation, I'm going to show you like a video of how it works. But basically, you can create adversarial examples in your shell as you are basically using Metasploit. If some of you is aware of, is confident, sorry, knows this tool that is Metasploit. And then finally, this is something that is still work in progress, but it's happening like right now in these weeks. We are integrating this tool inside Microsoft Counterfeit, which is basically a tool for assessing the robustness of your classifier and typing attacks in the shell. So that's going to be like a very, very good thing for the library, because it's going to be like used maybe for many people. So all of the things that I told you before are implemented here. So you can find all of the attacks and these 4 steps for the gradient base and the 3 steps for the black box things inside this library that we use in our work for testing the malware classifier we are trying to break, or trying to, understand how much they are robust or not. So, but in particular, which malware detectors? Because now I told you like, hey, security, machine learning plus security, I break classifier, I did this and that. And then I'm not telling you what we are actually attacking. So let's split the word in 2. We have the word on the left, that is the word of deep learning. And in the world of deep learning, we have basically different architectures. Here, we are just going to report the 2 that we tested, but there are like really a lot of networks for doing malware detection. If you just go on Google Scholar and type deep learning for malware detection, the list is long. But these are the 2 that we tested. So there is this one called malconv, which takes 1 megabyte in input. So you take your malware, you take the first 1 megabyte of content, and that's your input. And you then feed it to the network, and it's gonna reply with malware or goodware. And since bytes do not have any kind of metric, so what does it mean that you take like byte number 2 and byte number 90 and you do like 3 minus 90? This does make no sense. So for letting the network learn something relevant, they apply like a feature extraction part that is an embedding in a 8-dimensional embedding space. Then there is like a notion of distance, and then you can do training and gradients and whatever. Then another architecture, which is called, we call DNN lean or ReLU, depending on the activation function they're using, are, a bit smaller because they only take like 100 kilobyte in input. And again, they embed bytes for the same reason I told you. And it's just, it's just like a smaller network, but it has many convolutions more than malconv. So basically in some research paper, they show that this network basically learned like position of relevant things inside the header, like, oh, this is the PE header, this is the offset, and yada yada. Now we move to the word on the right. It is the word of like standard learning with feature extractions. So we take these gradient boosting decision tree trained on static features. And by static features, we mean features that are extracted from the structure of the file. So you don't run the malware, you just look at the file, and then you just, you pick the information you need, you build up this vector, and you feed it inside this tree. And for the information you might use are like the sections, the bytes, the entropy, the strings, and you can be wild. So these are the 2 words that you were using. So just to give you a recap, we take these guys, and before attacking them, we evaluate their performance. Because if you attack a network and this network already sucks, what does it mean to attack it with an adversarial attack? Because it's already broken by itself. So what we do is take different scenarios, and we just plot this ROC curve on the Ember dataset. The Ember dataset is just an open source dataset that has been used for training some of these guys. So as you can see, the brown thing that is the tree is kind of on top of every deep neural network. And that's kind of intuitive because the tree is not tasked to learn the representation, but is just focused on what the developers are feeding to it. So there is already domain knowledge on the tree. And while the networks that are basically trained on two different settings, some networks are trained on a proprietary dataset. It is like 16 million of samples. And the other ones are trained on this Ember dataset, which is like less than 1 million. And as you can see, the red and the orange, which are the one trained on the proprietary dataset, are not as good as the others because maybe the function that must be learned from that amount of data is too complex for the architecture of the network. So, and basically, this basically shows that you can have like millions of data, but then you have, the same architecture maybe might not be, useful for that amount of data. So with this in mind, I can finally show you some experimental results of the attacks that that are encoded in RAMEN against this network. We are going to start with gradient-based attack, and we are going to take the manipulation that edit all of the DOS header. So what the attacker does is taking this guy. It's not considering the MZ, that is the magic, and the offset, but everything in the middle is still editable. So the attacker basically computes the gradient, and for each byte, it starts replacing the values. And iteration over iteration, we can see that basically most of the networks are characterized by this slow trend that goes down. So this is like a modest detection rate. A modest decrementing detection rate, but still, as you can see, like Malconf is kind of defeated after like few iterations because its detection rate goes from 100 to 30%. It means that 7 malware over 10, evades detection. And these are kind of a lot. But the nice results are happening right now. So instead of just editing the DOS header, we are extending the DOS header, and then we fill it with bytes. And basically, this is enough for flatlining all of the models. Why? If you have a network that is trained only on bytes, the network is going to learning that at position X, there is the P of the PE magic, then there is the E, then a 0, 0, and whatever. If you shift this thing, the network is not aware of the context. So instead of finding a P, it's finding like, a Z, and that is gonna be, it's gonna weight differently when you compute the score, the malware score. And that's why you have basically this total decrement of the performances, again, from 100% to almost 0 for many of them. And finally, instead of editing the DOS header, we just don't want to, think about the header anymore. We just want to, shift content and then place adversarial payload there. And basically, the same happens. So you're destroying all of the local patterns that these network learned, except of that Malconf. And you might say, wait, Luca, you showed us that Malconf was defeated and defeated and defeated. Why it's up here? The point is that and I'm laughing a bit because it's kind of trivial when you look at it. When you opened and we debugged the attack, we found that in that region, the gradient is 0. It means that the network itself is not attributing any importances to that particular position. And then we thought, wait, what was there? And that was the first part of the code. So basically, this network has a vulnerability that is, if you edit just the header, the DOS header, if you want just to be sure, you're already evading the classifier. You don't need to do anything more fancy than that. That's why. So that's why this guy is like 80% detection rate. It's not because it's robust. It's just because the network understood that there is nothing useful. But it's not because there is the code. Anyway. Okay, so I hope I convinced you that gradient-based attack against deep networks are kind of effective. I'll let you judge by yourself from the results. And then we go to the gradient-free thing. So we take gamma, And we test it against the tree, because again, the tree is not differentiable. We can do gradient-based attacks on the tree, and Malcolm. And we do the following experiment. We extract 75 goodware sections from, and these sections have like read-only data. You can think about strings, the hello word strings I was mentioning before. And then we inject it inside the malware, and we test the performance of the classifier. So each of these plots can be read in this way. On the y-axis, you have the detection rate of the model. On the x-axis, you have the size of the attack, I mean in bytes. And then each line is basically a combination of the number of queries and how much I want to constrain the size of the manipulation. Then that's basically that C term that I told you before. So as you can see, the more queries I use, the more the optimizer is able to find smaller and smaller payloads that still evade detection. And you can just forget about Malcolm on the right, because as you can see, basically each of the thing achieve like 9 evasion over 10. So you can already forget about it. But the nice thing is that the tree that, as you can see, was basically the more robust when we did the ROC performance, here is, for some of the scenarios, as a detection rate decreased to 20%. It means that by injecting goodware content, we are able to evade 8 times over 10 these robust classifier. So we went wilder. So we thought something like, hey, what if these attacks might transfer to other products? Maybe they don't even use machine learning. We don't know. So what we do, we take ViewsTotal. ViewsTotal is an online service that hosts many commercial products. And what you do, you take a malware, or a file, you drop it, and it launches like 60 different products that are scanning your thing and saying, hey, it's okay, no, it's a malware. And we did the same thing. So we optimize attacks against the tree with the section injection attack that I told you before. And then, and with that, we also take the same malware and we basically add random content at the end. And then we send both of these guys to VirusTotal and see what happens. So this table is basically a summary of the results of our attacks. And we just put here 9 products that are kind of famous. And for the obvious reason, we are anonymizing them because, these are, like for vulnerability disclosure thing. And we also send something to one of this company, and we are also currently under NDA. So, I can't disclose too much. But the point is that among these, there are people that you actually use deep learning technologies for detecting malware. And as you can see, on the first column is the original detection rate that is like kind of high on our simple data set, like 100. Basically, we test this with like 200 malwares just to see what happens. But then we were kind of shocked because already the random attack were kind of effective. And that might be because, that the reason might lie in the fact that many of these guys use just the hash of the file to see, okay, this is malware because I know that this hash is malware. But then the very surprising result was found while we use the section injection attack. CAV1, it passes from 93% of detection rate to 30%. It means that the adversarial attack is able to transfer to a product that may be somewhere, on the device of someone. And that's interesting, but also kind of scary to my point of view. So I think that this is relevant for the community because you might need to test the performance of your classifier with these tools. So you might ask, how can I do that? So you can use ToucanStrike, which is the tool that basically we created. It's again written on Python, and it's able to, so you take a target, in this case malconf, a malware like the PTR ransomware, and you can just predict and see, okay, the malware is recognized as malware. Then what you want to do, you create an attack, in this case, the partial DOS attack, so the attack that edits all the header, and then you just hit run. And you just wait until, in this case, there are only few iterations, but basically on the background is processing the file and it's editing like the values the DOS header. And at the end of the optimization process, what happens is that this network in particular is evaded, and the score is 0.02. So from 91% to 2% of being seen as malware. That's kind of a difference. So, okay, to conclude, we propose this general framework called RAMEN that is useful and is basically focused on targeting and generating attacks on the security domain. Then I showed you the concept of practical manipulations that are used for avoid the usages of sandboxes, and how you can manipulate the Windows PE file format, which is basically a gold mine of things that you can try, because there are already, there are a lot of things that you can do with the format and exploit the format itself. Then we released and we showed you how we can, the library that is SecML Malware that is connected to ToucanStrike, and the fact that we have this counterfeit pull request is already in progress, and you are free to use it. You just type on GitHub and you're gonna find it if you want to test it. And the final thing that, one of the final key points that I want you to take away is that detectors are really vulnerable to adversarial examples. And we might understand how to catch this thing while either testing the robustness and finding new attacks and understanding what the defender can do from this point on. As a limitation, exactly how can I do from defending from this attack? Well, some of the manipulation that I told you today can be stripped away. So if you know them, you can strip them. So that's why you need to study them. And then these attacks that I showed you are only static in the sense that I'm not targeting detectors that are basically taking information from the trace of execution. And that's exactly the future work we want to, we're aiming to. So we would really like to break classifiers that trace execution, that traces internet traffic and more. So how can we create adversarial attacks on that? That's something that we want to investigate. Then we might want to mess with file formats again. Sorry, that's my timer. So that we would like to mess more with the file format, like we take the PE file structure and we really, hammer it down again. And finally, maybe we would really like to test more domains, like what happens in Android domain. So I hope I've convinced you. I convinced you. I really thank you for the attention, and I really hope this talk was interesting to you. I'm done.
Great, thanks, Luca. So great talk. We have a question from the YouTube stream, so maybe we can take that first.
Yes, let's go.
Okay, so Adam asks, instead of genetic algorithm or RL, is it also possible to apply Bayesian optimization for efficiently reducing search space for black box manipulation?
So you mean like creating a distribution and then sampling from it, something like that, I think. The real answer is that I don't know. And that's something that you might investigate, because, let me say better. It depends on how you parameterize the manipulations. So if you find a way for parameterize the manipulation and create like a distribution, then you can sample it, and maybe that's going to be useful for the reconstruction problem. So the real answer is yes and no. No, it's not here at the moment. Yes, it might be.
Okay, thanks. All right, so I'm going to